Okay, good afternoon, everybody. So this is the second tutorial for the Fluids 1 module. So Zutong couldn't come today, so you'll have me doing the tutorials today. So first of all, there are 6 questions in today's tutorial. Is there any question you would prefer me to do first, or should I just go through them in order? In order? Yeah? Okay. So let's start with question 1. So question 1 presents this manometer and asks what is the pressure at point A. So the best way to do any questions is first to start writing what do we know and what do we want to know. So in this case, we know that this is water, this is mercury. We know that the density of water is 1,000 kilograms cubic meter. Yeah. We know that the specific gravity of mercury is 13.6056, and this is the density of mercury divided by the density of water. So then the density of mercury would be this okay. We know that gravity is 9.81 meters second square, and we want to know the pressure at A, which I call PA. Okay. And we also know that the hydrostatic pressure P is rho GH. Okay. So whoops, sorry. The second step, this tube has different sections, so it's good to label them. So we call this, for example, D. Then after the drop, we call C double prime, C, no, C prime, sorry. Then that's C. Then that's B prime, B, and finally A. The letters you can put anything, it's just to label. Okay. I forgot to say, but if you have any questions at any point, just ask. Okay. So, the first step, the pressure here is the atmospheric pressure, the pressure in D, so PD is P atmospheric. Okay, and then we can follow the columns to see at each point what is on top of that point to know and use the formula to calculate the pressure. So in C prime would be the pressure at D, which is the atmospheric pressure, plus this distance, so the density of water by gravity by this height. So then it would be density of water multiplied by gravity multiplied by 0.25. It's important to have all the units always in the international system. Okay. So then next we have C prime, but because C prime and C are at the same height, there's no change in pressure. So the pressure at C will be equal to the pressure at C prime. No, sorry. The pressure at C prime would be equal to the pressure at C double prime. So this is equal to this. Then between C prime and C, they are at different heights, but the tube is filled with air. And what happens here is that the density of air is much lower than the density of water or mercury. So we can disregard the change of pressure during the air section. So then this will be the same as the pressure at C. But then we get into B prime, and B prime has a column of mercury on top of it. So then the pressure at B prime would be the pressure at C plus the density of mercury multiplied by gravity multiplied by this distance. Okay. And then again, because B prime and B are at the same height, the pressure at B prime is the same as the pressure at B. Okay, so now we've reached B looking in this direction. So we've solved from the atmospheric pressure to B. But then if we look in this direction from B to A, the pressure that we calculate in this section has to be the same as the pressure we calculate in this section, because it's the same point B. So if we look at PB again, is this? No. Okay. If we look at PB, it has these 70 centimeters of water on top, and then that is the height of A. So the pressure at B, it's also the raw density of water multiplied by gravity multiplied by 0.7. Okay, plus the pressure at A. And the pressure at A is what we want to know. So if we put these two together, yeah. So we get that pressure at C, which, well, I can put it together and then write it. So pressure at C plus rho mercury plus G plus 0.3 is equal to rho W G 0.7 plus the pressure at I. And we know, so then we can isolate the pressure at A from here. So you get, whoops, yeah. Okay, and then we know that the pressure at C, where it was, pressure at C is just the atmospheric pressure, so plus rho water G 0.25 plus rho mercury G 0.3 minus rho water G 0.7. This is equal to the pressure at A. Yeah. And then we could just substitute the values here, or we can make it a bit more, well, we can group terms together if we want. So we get the atmospheric pressure plus WG 0.25 minus 0.7 plus rho mg 0.3 is equals to the pressure at A. And if we substitute the values, we have raw water is 1,000, gravity is 9.81, then the density of mercury, and this is equal to pi A. And if you calculate this, you get that PA is equals to the atmospheric pressure plus 35.5 kilonewtons meter. So this is the absolute pressure at A. And then, because we don't, well, we can calculate also the gauge pressure, which is what we should do in this exercise, which would be the same without. So this is the total pressure. Oops, total pressure. So then the gauge pressure, yeah, it's the difference between the pressure at D and the pressure at A, which would be just the 35.5 kilonewton meters. And that is the answer. Is there any questions? Yeah. Yeah. Yes? Oh, yeah. So the specific gravity of anything is the density of that fluid divided by the density of water. So the question gives us. It doesn't give us the density of mercury. It gives us the specific gravity of mercury. So that would be the gravity of mercury divided, the density of mercury divided by the density of water. So this is why I divided them. And then the density of mercury would be the specific gravity of mercury multiplied by the density of water, which is what I did. Yeah? Okay. Any other questions? No? Okay. So then I'll do question 2. So question 2 says, due to the gradual setting of sediment in a tank, the density of brackish water varies with depth according to this formula, where Y is the depth below the free surface. What is the gauge pressure at the bottom of the tank if the liquid depth is 1 meter? So we don't have a picture for this one, but we can draw one easily. As always, first write what we know. Yeah?
I think I have an idea on how to address this question.
Okay.
Because of how the density is within a function. The hydrostatic equation is equal to the integral of rho g with respect to the depth between the upper depth and the lower depth.
Mm-hmm.
In this case, rho is a function of z. Rho is a function of depth yeah, and G is still a constant because of the small distances we're addressing. So you have to integrate P, then you have to find the value of the magnitude of the area below the definite integral of rho between P0 and 1. So int rho 1 minus int rho 0 is equal to something. You multiply that something by G, and that's how you get the pressure.
Yeah, that's correct. So you have to integrate the density. So we cannot use the rho GH that we were using in the previous exercise because rho is not a constant in this case. So we have to use the general equation which asks us to integrate. So this is what I'm going to do now. So we have our tank. Oops. No. Okay. So this is the atmospheric pressure on the top of the tank. Then the length is 1 meter. And then this is the depth y. So the density follows this formula. Okay. And then it's asking us the gauge pressure at 1 meter. The gauge pressure, it means the difference between the pressure at the top and at the bottom, so without taking into account the atmospheric pressure. So then we know that the hydrostatic equation for when the pressure is not constant, it's partial of pressure divided by partial of depth, it's equal rho g. But in this case, the density depends on y, which is the distance from the surface. But the hydrostatic equation is on z, and z is the depth, so the distance from the bottom to the surface. So in this case, it could be better for us, more convenient, since rho depends on y, to have this hydrostatic equation depending on y also instead of z. But the relationship between z and y is that z is equals minus y, so we can just go partial p, partial y. Oh, sorry. It's equal rho g. So I've removed the minus sign because the distance, the directions are in the opposite direction. Okay. No. So now what we have to do is just integrate. So, and between 0, this is y equals 0 and y equals 1. Okay. So the variation in pressure is the integral between 0 and 1 of 1,000 1 plus 0.2 y multiplied by g and dy. Okay. So then integrating this is just a polynomial. So the 1000 is constant, G is constant, so we can take it outside. So 1 becomes y, and 0.2y becomes 0.2y squared divided by 2. And this is between 0 and 1. So then this is equal, well, yeah, you just substitute the numbers. Oh, sorry, I forgot the G. Substitute the numbers, and it's 1000 multiplied by 9.81. This is 1 plus 0.2 divided by 2. And this is equal to 10791 pascals, so more or less 10.8 kilopascals. And this is the gauge pressure at 1 meter. Yeah. Yes? Sorry, could you repeat the question, please?
How do we know when we're supposed to use hydrostatic equation?
Oh, okay. So instead of the one we used in the previous, so this, we had to use this one because the density was not a constant. So in the other one we had density of mercury or water, which were constant. But in this case it's not. So then we have to use it.
How do you know it's not constant?
Because it follows an equation that depends on y. It's not just a number, but it depends on a variable. In this case, the distance from the surface. Okay. Any other questions? No. Okay. So I'll just go to question 3. Oops. Okay. So question 3 is this incline manometer, and it says it's filled with oil with a specific gravity of 0.85. The cistern is initially open to the atmosphere, and then a pressure line is then connected that creates a gauge pressure of 500 pascals. And then the oil surface in the manometer tube is displaced by a distance of 200 millimeters, and it asks for the manometer angle alpha. Okay. So as always, let's see what we know. So what is happening here is that at the beginning, this is open to the atmosphere, and this side is open to the atmosphere. Because both sides are open to the atmosphere, then the pressure here is the same as the pressure here. So we call this B and this B prime. So the pressure here and here is the same, but then they connect a gauge pressure here of, what does it say, 500 pascals. and what it does is it lowers the oil. So because the pressure is bigger than than before, it lowers the oil to this C point, and then pressure at C is 500 pascals. So then, because this pressure pushed the oil down, this oil will move through the tube, and this is the displacement in the tube. So the displacement in what I called HBC, which is this distance, the volume that you've displaced here will be the same volume as the oil moves here, because it's incompressible. And we will use this a bit later in the exercise. So then I will call this point A and this point, just stay, and this point B, and then this is alpha, and then this is the diameter of the tube, which I called dt, and this is the diameter of the tank, which I will call dt capital letters. Okay, so as before, and I will call the distance just d, the distance that the oil moves. Again, we got given the specific gravity of oil, so then the density of the oil will be 0.85 multiplied by the density of water, that is 1,000, so it would be 850 kilograms meter cubic. Okay, so so now that the oil has moved, we can check what is the pressure. And they are asking us for what is this angle, the angle of the tube. So what is the pressure at B? So the pressure at B is the pressure at A, which is just the atmospheric pressure, plus plus the rho of oil, G multiplied by HAB. Yeah. And in this case, HAB is not, it's not D, because that is diagonal, and we only want like pressure in the, distance in the vertical direction. So then HAB will be this distance D, multiplied by the sinus of alpha, because this angle is the same as this angle. Yeah. So this is the pressure at B. And we know that the pressure at C, like here, here is the pressure at B, yes, plus the density of the oil, G, and this distance here, which is HB prime C. But we don't know what this distance is. The problem doesn't specify so. So how can we get HBC? So we know, as I said before, that the volume of oil displaced in here is the same as the volume of oil displaced in this part. And we know this distance. So then what we can do is say, well, the volume displaced in the tank, which I will call just volume tank, it's the area of the tank multiplied by this distance. Yeah, and the area of the tank, it's pi by dt square, well, dt divided by 2 square, and then the volume of the fluid dispersed here, which I will call volume tube, it's the same, pi, but the like lowercase t divided by 2 square, and multiply by d, which is this distance. Oh, sorry, I forgot. Yeah? Okay. So now we know that these two volumes have to be the same. So then we can just put these two equations together. So pi dt squared divided by 2 by HBC prime is equal to pi dt divided by 2 squared by d. So then from here we can isolate HBC. Yep. Okay, so then just HBC is dt squared by d divided by capital D square. Yeah. So now that we have this, we can put it into this equation. Yeah. Wait a minute. Sorry. Yes. Yes, okay. We can put this equation into this and then get the whole thing. Yes, so you get that PC is raw oil G D sinus of alpha, because this is PV, plus the atmospheric pressure, and then plus raw oil G, and then dt squared multiplied by d divided by dt squared. Yeah? Okay. So then the only thing you have to do here first is we are not using the atmospheric pressure. Oh, sorry. Yeah. We know what the gauge pressure in PC is. So because they say gauge pressure, it means that is the pressure in here without taking into account the atmospheric pressure. So we can just neglect the atmospheric pressure here. And then we have all the data, we know the density of the oil, we know the distance, we know the diameters and the distance, so we can isolate alpha from this equation. And I have to have it around here. So, well, first you can say that PC is rho oil GD sinus alpha plus rho oil G dt squared D divided by dt squared. So then sinus alpha here. Is PC divided by rho 0 G D minus dt squared divided by dt, and this is 0.04981, and then if you do the arcsinus of this, alpha is 2.85 degrees. Yeah, you? It says in the question. So it says that a pressure line is then connected that creates a gauge pressure of 500 pascals. So this is the pressure at sea. Is like it is first open to the atmosphere. So, it is first open to the atmosphere. So the line is here, and then it pushes it so it's behind the B level. And this pressure that pushes the oil down is the pressure at this line, and it's this 500 pascals that says in the question. The difference. So the pressure at B was the pressure that was before when you had it open to the atmosphere. And then it's like, it says they connect something here that makes the pressure be higher. And this is the 500 pascals. And this pushes the oil to the sea level. Yeah, okay. Yeah? PC equal PV rho GHBC. The second one. The volume. The formula for the volume.
Density of oil and gravity inside.
Density. Oh, this one. Yeah, because I say here that PC is PV multiplied by rho oil HBC, and then here we calculated that PV is the atmospheric pressure multiplied by the density G HAB. And HAB is the sinus of alpha. Yeah?
If you just go down, you know where you factorize the density of oil with GD?
But, oh, yeah, here.
Why is there still density in the bracket then? Multiplying it out.
Oh, sorry. Yes. My mistake, thank you.
And then don't you have to put the D inside the bracket as well because it's not multiplied by the second
Yes, or just take it out of the bracket entirely. Yeah, sorry about that. Thank you.
Why do we cancel atmospheric pressure?
Sorry? Oh, because it's gauge pressure. And gauge pressure means without atmospheric pressure. Yes? Sorry, I cannot hear you properly. The last one? This one? Oh, sine of alpha. Oh, yes. Thank you. Yeah, I forgot the square. Oh, yeah.
What do you mean by dt?
Oh, so is the name I gave to the diameter. So the lower case is the diameter of the tube, and the upper case is the diameter of the tongue. Yeah. Okay, any more questions? Yes.
How do you properly find HAB of d sine alpha? So we know we have d.
Yeah, but you don't calculate, so alpha is what we want to know. So you don't really calculate HAB. You put it in the formula as d sinus alpha, and then you just keep it as d sinus alpha, and then at the end you isolate sinus alpha, and you get alpha. Yeah? Okay. Any more questions? Okay, so okay, so let's go for question 4. I've just seen there's only 15 minutes left for the tutorial, so would you like me to do any of the other questions?
Can you go for 5?
5? Yeah? Okay, I'll do 5 first. Whoops. Okay. So in question 5, we have this dam that says it's 40 meters wide into the paper and is made of concrete and weighs whatever it 22 kilonewtons meter cube. And then assuming that the density of water is 1,000 kilograms meter cube, calculate the pressure force on surface AB, and the atmospheric pressure is 100 kilopascals. So if we start to write what we know, so we have, so this is the atmospheric pressure, and we know that the atmospheric pressure is 100, so 100 per 3 pascals. The density of water is 1,000 meter cubic. And that's it. Oh, and the width is 40 meters. And then we have the height, which is 80, and the length, which is 60. And we want to calculate the pressure on this surface of the dam. Okay. The pressure. Oh, yeah, the width is 60 and the height is 80. No, because 40 this is 3D. So there is a dimension that is not represented here, which is the dimension inside the paper, and this is the width. Okay. So in this case, we know that the force is the pressure at the center of gravity of the face of the dam, and then multiply by the area of the face. Okay. So there are two ways of doing this. I will just do one, and then if you want me to do the other, I can do two. Okay, so the first way is static calculating. Well, if you have this dam like this, the center of gravity of the face would be at half the distance. So this is the center of gravity. So the depth to the center of gravity, which I will call h, is 40 meters. Okay? Yeah. Okay. So then the pressure at the center of gravity is like we were doing before. So what's on top of this center of gravity? We have the atmospheric pressure, and then all the pressure of the water on top of the dam. And this pressure is rho g h. Okay, and we know all these values. And then the area is the area of the whole face. So we don't know what this distance measures, so we have to calculate it. But because we know these two, we can just use the Pythagoras Theorem and go is like 60 squared plus 80 squared, the square root, which is the distance from A to B, and this multiplied by the width of the dam. So you multiply it by 40. Okay, well, I just realized I did all this with numbers, but if you do it with, so this is dBc squared plus dAc squared and the square root multiplied by WD. Yeah. So then if we just substitute the values, we have that the P at Cg is equals to there you go. The atmospheric pressure, so 110 to the 3 plus 1,000 plus 9.81, which is the gravity, multiplied by h, which is 40. And this is 4925 400 pascals. And then the area. Hmm? No, the age is 40 because it's 80 divided by 2. Yeah. Oh, okay. So then the area is 4,000 meters squared. So then F is P CG multiplied by the area. So is 1.9696 10 to the 9 newtons, so more or less 2 giganewtons. This is the F. So that's it for this one. The last one? No, it's a multiplication, sorry. Yeah. So the force is pressure multiplied by area. Yeah.
Why is the centre of gravity height 40? For a triangle, is it 2/3?
Because you are not doing, it's not the center of gravity of this space. It's the center of gravity of the face of the dam, which is a square. Yeah, so it's in the half of it. Any more questions? Yeah. Yes, down. Yes? Yeah, no, you don't need it because the only thing that is the only... Okay, you want to know the pressure at the top of... Oops, sorry. You want to know the pressure at the top of the dam, so how much the dam weighs is irrelevant. You only want to know what's on top of it. Yes?
You know how you said there was another way to do it?
Yes.
Is it quicker?
No, it's not quicker. You'll have it in the, when we publish the solutions have the two ways. So, yeah. Yeah? It's 1.9696 10 to the 9. So this is giganewtons because it's the 10 to the 9. Yeah. Yes? Sorry, could you repeat the question, please? So if they would ask you for the pressure at the, like here, at the bottom of the dam, then the weight would be relevant. But they ask you for the pressure at the top of the dam. So there is no concrete on top of this point, so then the weight doesn't matter. Okay, so is there any